Okay, so welcome back to the second part of our lecture 4, Virtualization and Data Center Design today as part of our Cloud Computing and Big Data course. So virtualization is a big term in cloud computing. I think by now you noticed, although we just scratched the surface of some techniques which are very basic, like live migration, the abstraction concept from real physical hardware to do logical hardware or virtualized hardware, and then sharing this with many at economics of scale. And this economics of scale is something I would try to put an emphasis on when we now have the second part, which but still is really based on the virtualization again. So you will hardly find any cloud data center which really scales from Facebook, from Google, wherever it's providing, that is not based on virtualization. So let's have a look a little bit how we now think about this in a larger scale, right? So people like Borealis, when we go there, they probably will also talk to you about virtualization. And of course, then it becomes a little bit more real. Admittedly, this is a conceptual way, how we teach this here a little bit, but you have seen in the video already some analogy. And basically we have at the end here a video inside a Google data center that then also will basically reflect on these boxes that you see here. Because these boxes that you see here are, of course, really racks, right? So very dense setups of multi-cores and many cores together with storage, memory, etc. And then rack by rack close to each other inside a data center. I have some pictures to show you, and I'm not sure, was someone from you already in a data center? I mean, you probably, but some of you maybe know, right, how that looks like. Now, the point is it's physical hardware. That's why we have, of course, this kind of interesting boxes there. The way we use it, however, is really much like you see it here, right, in different colors. So the color encoding stands essentially for virtual clusters that can span different physical ones, that can, let's say, cut some of these from the physical way out to have it dedicated for some other virtual cluster. And this is the power of virtualization. By doing so, and the video was alluding to it, we increase the resource utilization. Why? Because basically here you have now the full flexibility of using the physical clusters to the best of the applications. If you would have, let's say, one example would be having a physical cluster just for Apache Spark, another cluster just for Apache Hadoop, and another cluster just for the R server, right, for doing statistical computing with R. Then the users will basically use Spark, but nobody's using Hadoop. The whole cluster will be empty. Nobody's using it, right? Our people maybe right now using Spark. Maybe tomorrow they will use Hadoop again. But then basically you have a whole physical cluster idle. Again, of course, think about what we said. It costs a lot of money to buy the hardware. Having it just lying there, nobody's using it, is basically the total cost of ownership very, very bad for a company. Hence, making it virtualized is, of course, good step if you have on-premise resources. The next step, as you have seen in the video, you go completely in the cloud, then you don't have any of the total cost of ownership, no physical cluster at your site. But of course, in the Google Cloud or the Facebook Cloud, whatever cloud there is, they do the same principles, but basically that you don't really experience it. But this is a very important part in it. And has basically achieved now really a production status that automatic deployment, this was also a little bit with the VMware video, basically have a huge infrastructure from management perspective around it. So that really look up times, down times, deployment, hot deployment, live migration, that this is all built by users, different users. It is actually one of the most interesting ones is then this virtualized network that you maybe have seen in the video. At the very end, they said, of course, you have a physical interconnect, but you can now do basically virtualized networking as well. Let's say allowing some users the access to some cluster parts and others not. That could be relevant for medical applications. You have medical data in the cloud, but only one fraction of this cloud is really accessible essentially from let's say, the other parts of the cluster. We will talk about this, and the video again was alluding to it. Hybrid clouds is a big point where you have on-premise resources combined with those which are somewhere in the cloud. That's what's called hybrid cloud, and we will end today a little bit about it. But essentially still the concepts of virtualization remain no matter how you deploy it. So by having this virtual clusters, basically the same principles goes that we have already seen in the small setups in the first part. So of course there will be lots of repetition. You need a virtual machine manager, someone who's really managing all of this. You have basically these clusters very nice connected and can swap. But as you've seen here, basically now that looks like when you think about from the real perspective of virtual versus the real physical ones, you would say that you basically have here virtual cluster nodes from this and this for this particular application D. And you basically create now the virtual clusters across the physical ones. And with this, you can shrink up, shrink down, can basically do this cloud elastic flexible behavior that we know of, especially if you think now about live migration. You would say here, for instance, maybe this would be at some point in time too much overload for physical hardware. So why not doing a next physical hardware and shifting 2 of these VMs just on that, right? With virtualization, with the abstraction layer, that's very simple possible, something we have learned with live migration. So for the load balancing, that's what I'm talking about. It's another interesting idea to partitionize essentially into virtual clusters so that you can better load balance. Then, of course, the failure of the physical nodes, let's say this will be going down very quickly for some, let's say, CPU overheating, whatever it is. Then basically with live migration, of course, needless to say, we can shift quickly these parts of the virtual cluster away as well. Equally, if you think about, we would have not virtualization, let's say in the Spark physical cluster that we wanted to have here. We said, as an example, this might be just a Spark cluster completely alone, no virtualization. If there's some break here in terms of overheated CPUs, no one can use a Spark cluster. It's broken, right? And that for a day or two could be a problem. Of course, think about that, as I said, hardware fails all the time, but people not repairing all the time, right? So the hardware stays usually a couple of days with errors, with problems. Of course, the big players like Facebook and Google, they have some roller people that go through the data center and actually do then, you know, the hardware kind of repairing, but even that is slower than the hardware breaks, right? Usually they're maintenance windows where then basically lots of this hardware is exchanged. But we will talk about this a little bit also later. So it's very interesting ideas, and here just the idea that basically all cloud providers have adopted this functionality. AWS, Microsoft Azure, and the Google Cloud Platform also used basically for lots of apps. As you see here a little bit the comparison to the Google App Engine that we also will look in some of the later courses when we talk platform as a service. And this is on different service levels. Now, I talked a lot of CPU fails. Storage could be the same idea. So we will also look in the next couple of lectures in all the different ideas how we can do storage. We start with a distributed Hadoop file system, but then you will see also here things like elastic block storage or simple databases, things we basically look in different services, but they're all basically based on this virtualization idea, making it possible to really do this. But we will have much more info on this in lecture 8, 9, 10 of all of these different ideas. But it's really, let's say, penetrate every part of a data center, this virtualization concept. Now, thinking again about the cost models, why now doing this? And why thinking about clouds in general? Maybe you are basically in a company and have to decide, right? So why we should do this? In a way, you can see it directly with these two ideas, how you can basically compare, of course, a cost. Usually you have this kind of total cost of ownership, or your basically costs in equipment. So here you buy really physical hardware, right? And then on top of this, you could say there's some cost increasing with the number of users. That is always something which you can expect usually. But you see, of course, this is the traditional IT. You have basically on-premise, as we call that, your server, your Spark cluster, your physical devices. And of course, the idea of cloud computing is now doing essentially this. You just pay for the dynamic parts, pay per use. The more users you have, the more Spark cluster parts or workers you need, the more you pay, right? So basically, you get rid of this fixed costs, and that's why basically do this. Also think about that, of course, some startups maybe don't even have the capital of doing this, right? Because buying a big Spark cluster that is quite powerful, that you really want to use maybe on a daily basis, costs hell a lot of money. And this needs lots of investor capital that you maybe need rather for people, rather for IT equipment. And with the success of the company growing a number of users, usually you can slowly scale up and slowly actually more or less grow with your IT, right? Which you cannot in the normal principle way, because if you buy a cluster your own, you have to have the whole building for it, the infrastructure for it. Usually also you have to think about fire, right? We basically drop out fires with gas, not with water, obviously, right? Because water would be very bad for hardware. So lots of considerations that as a small company, you usually would say it's lots of money. Plus you need administrators, right? Many of them, 2 or 3 maybe, that set up the Spark cluster, that know something about security patches, operating systems. So lots of expenses, which you usually have just in the cloud. And this motivates a little bit, of course, basically this part. On top, which is often forgotten, is that when you now think about deep learning, the hype using GPUs, many cores, right? They have a Kepler machine. Basically, you buy the Kepler cluster, it's a generation of a GPU. Today, nobody wants this anymore. Everybody wants an Ampere 100, right? Or at least a very cutting edge, like a V100 Volta architecture in GPUs. So that means every 5 to 6 years, we already know in IT that basically the IT will be so renewed that we have to throw the old stuff away, right? And get a new cluster. Otherwise, it doesn't make sense. What you can learn now with deep learning on an A100 compared to this in a K40 or K80 cluster where I was computing 6 years ago is a major, major difference. They have tensor cores. You will learn in one of the next lectures. But long story short, this is even more dramatic, right? The first one, because you can assume that on top of these costs in 5 years, you have a next cost you have to do. And then basically you have to maybe relearn the people to new technology. And with this, basically this cost model is harder and harder to do. Of course, for security consideration, this might be your only model, right? Hence a hospital. You see rarely hospitals, at least in Germany, I know, that have basically their medical data in the cloud because you have to have it on premise, right? If there's a security problem and all your medical data gets exposed somewhere in MS Azure, you know, that's a big issue. Hence, there will be always institutions which have still something on premise, but the point is that you can combine this in the hybrid clouds, as I said later. And for some parts, you maybe have a fixed cost reduction where you're saying some things I can really share in the cloud, no problem. Let's say maybe billings or so you can do in the cloud, while the real work on medical data has to be basically on premise. But this is now the idea, how you think about more of this cost model. Of course, there are small letters, as I said, when you run a Spark cluster and you're not using it, still charged all the time. This is something also what, of course, could kill a startup very quickly if they don't shut down the Apache Spark cluster, for instance, directly if it's not used or so. Hence, you need someone monitoring this. Now, another view is here basically infrastructure costs. This is a little bit in the past, but that doesn't really is basically giving any problem here. The same idea remain, that you essentially have this kind of idea of physical servers that you basically have at some point, of course, really to buy, but with the costs then basically of having, you know, logical servers much, much more available, basically that you can expose to your customers and then have better resource utilization, things we discussed. However, you also have to think about then in this context to contrast it better, the cost of cooling of the infrastructure, as I said, and this is quite nice, playing in the hand, basically, especially for here in Iceland and the Nordic countries, the cooling. So 1/3 of a data center is nothing else than cooling it down, because obviously it generates lots of heat. And this is very nice with ambient air cooling in Iceland, but also with cold water cooling. So different concepts available. And of course, helps us a lot instead of having a data center somewhere in Texas, right, where it's very hot all the time. Hence, you will see a movement to many of the Nordic countries from major players. The European supercomputer that is the most powerful is in Helsinki, theoretically, but it is really physically standing in Lumi in Kajaani, right? So it's an old paper mill very much in the north of Finland, because, of course, it's much, much, much more cooler there. Operated from Helsinki, of course, big capital, many people, smart people, but you can do that remotely. It's a good example how that works today. Equally, what we do here in Borealis, Reykjavik, managing a lot of things, but in Borealis data center, they operate in Blönduós, a big facility. Why? It's colder, it's directly close to a hydropower plant. So basically, even on top of that, it's not only that we miss a cooling, we also have hydropower. That means 100% renewable. And on top of this, what Blondos also is featuring, they have 100% renewable as a backup. We talk about this also soon. Of course, many of the large centers have diesel backups, right? When there's some energy failing, you need diesel generators. I talk about this. It's called here the UPS. We talk about this later. The emergency power. What happens if your main power fails? A question, yeah.
Russia is a very suitable place to put some stuff in as well, because there's good stuff for emergency power, and there are also a lot of very cold regions.
Yeah, Siberia, of course. Yeah, and I was on a Nordic conference not long ago, and actually Russia is doing there the most. In the Nordic, they have the best infrastructure there compared to everyone else. So really talking about the pole, right? This polar infrastructure, which is something to think about, because there we are all neighbors very quickly. It's not big distances. But yes, of course, cold regions, we talk very European way, Nordic, so talking Sweden, Iceland, Finland, Greenland, maybe in the future. But indeed, Russia and Alaska, and so on, basically also in the US, talking more about this is definitely a point. There is a small side remark, which also helps now Iceland, that we get a third channel in the ocean network. So that's something not to be forgotten, right? So talk about Siberia, somewhere in the nowhere, operating a data center with many different users in the world. They also need the network connection, right? To have, of course, networking, to shift the data, to do this. Here in Iceland, we get a third cable, would be beautiful, but also this is something what the Nordic countries have to think about. Just putting it, let's say, very much in the north is good for cooling. But firstly, you have some people have to live and work there to exchange the real hardware. It's also sometimes hard. But then, of course, the network needs to follow through to make that happening. And this could be issues. That's a new concept, which is also quite interesting. Yeah, indeed. Indeed. I think we will find lots of new models on that. I think one I have seen is also with this kind of devices that are lying at the ocean, right? So they generating power and having then close to the data center, there's basically ocean generated power, also completely renewable. But there's some concern that there may be animals and animal life will be destroyed. And it looks bad, of course. But the water cooling is one aspect of it, which is, one factor. I come to the question, but 1 second also is to consider other countries now have a whole system to work with the warm water that comes out of there for heating cities, right? So it's also not that bad of people saying, well, we have now a hot country and we have to give the data center away to the Nordic countries. Now, basically, all the, let's say, more hotter countries have more concepts of really using the water that is used from the supercomputer heated for district heating. So basically, you will find in the future whole cities parts completely heated just by the wastewater of a HPC machine, basically. But yeah, you had a question, yes. Yeah. Don't take it by heart, though. It's an example, but yes.
1/3 of the cost is for cooling.
Mm-hmm.
Is it mostly electricity needed, or is it also infrastructure?
It's both the chillers and, of course, also the energy needed for that. Basically, it depends again which is now your way how you cool it. There's basically ideas that between the racks we will learn this actually in a couple of slides, and we have the material and the visualization. It depends, of course, how you cool. There are different ways how to do it. We will reflect on some, but this is a kind of rule of thumb. You would say 1/3 is for cooling. Of course, this is now different when you place it in Iceland. Then you would say 1/3 is now taken by ambient air cooling. So this is then the factor that plays into it. But if you, let's say, put it somewhere in California, you would have basically these costs. And we will look at some ways how you cool basically the cluster now with air ventilation, cold air on the bottom, so that it basically, basically cools the clusters. But as I said, also there's water cooling these days, which is a bit different concept. Then there's immersive cooling. So you have the CPU in water, literally, right? It's a chemical substance that is basically especially prepared that the CPU is directly exposed to water. So there are different cooling mechanisms. But in the way, it's still, let's say, rule of thumb that you need this for cooling down. And this could be infrastructure cost, the chiller itself, and so on. Good. Yeah, but let's continue a little bit so that we get through the material. Just some metrics that we have to learn a little bit. I think that's important to think about it. This is something where I think one of the big metrics is that although you would say buying all the machines and having this there would be probably something which is the most cost of a data center, but that is indeed not true these days anymore. So hardware costs are basically relatively cheap, right? So you would say, again, rule of thumb, 1/3, or you see here 40% maybe, or something like this, is then the cost of a data center for the hardware. All the rest, infrastructure, maintenance, management, the cooling, the gas, right, for fire, things like that, which all needs to be considered. But we will see that when we go to the Borealis data center parts, that of course this is all specially prepared with double floors here and there where the network tables come through, etc., etc. So just take away the measures is important. Like 60% of the cost really is then just this maintenance management overhead that we have to do. And of course, now think about this again, when you have very small clusters and you have always 60% just the infrastructure. Now the idea of this, let's say hyperscalers at their costs, a Google data center which spans 10 soccer fields. The idea is now exactly that, to do this on economics of scale, to say, well, if it's anyway 60 costs of management maintenance there, then I should have lots of hardware that this gets me self-revenue, right? So it's much more cheaper to build basically then a very large 10 soccer field Google data center than operate your smaller data centers, because the 60% will be overwhelming again and again. Not talking about getting the right people to do the job. And this is basically stretching across many elements from power efficiency as well, basically up to many different, let's say, consideration we had in terms of chilling. Another part is, of course, that something you should consider is that GPUs basically are much more cost efficient these days, the accelerators, luckily, so to speak, otherwise you would never achieve probably exascale. Because nowadays we have not a problem again, basically in buying all of this and operating all of this hardware, but rather have energy for it in Europe, which is a big problem, not directly in Iceland. So that's very good for us, but it's a general problem. And there, basically the nice thing is that the GPUs running, if you remember, on 1,000 of these cores, but they have a very, let's say, lower clock frequency than the CPUs, and with this burn not so much energy, although there are many of them. And they operate essentially with the same idea on the chip already, with this economics of scale, many simple tasks very quickly. So yeah, GPUs are basically beautiful also, but of course, what we will also learn in later lectures, you cannot do everything with it, right? So some of the applications require still CPUs. You cannot do everything on a GPU. Just deep learning, machine learning is very popular, but many other things still require CPUs. So Microsoft is a good example. We had the water one, but the dominant ones are still basically on basically somewhere on the planet, here directly on the land. And here's an example that is around 10 times or 11 times of the size of a football field, right? So think about how large that is. And it has around 1 million servers. You see a little bit here already the kind of diesel generators and some chillers, basically, which have really big ventilation machines, something not you put just in a room, you know, basically that you know from our personalized chilling is really professional chillers that are there operating, that require, again, lots of energy, unfortunately, and the infrastructure piping it through that data center. But the point that is basically shown here is very good in the sense of saying, this is really economics of scale. You have the larger the data center is, the better it's basically to get revenue out of it. Although you have all the risks, obviously, one fire, the whole data center gone, or earthquake problem, etc., etc. Still, here's the problem, more rather of getting the best operational cost out. And this is what you can do in this economics of scale, really having rack by rack by rack by rack, which we also will see in the video. Hence, they are much more dense, right? You consider now basically something which you maybe know still from your desktop machines and computers. These are racks, and we will see this also in Borealis, where really a GPU is really stacked very close to each other, or CPUs with memory called racks. So the terminology is something which you should really know a little bit and basically get by heart. And there's a specialized industry that creates these racks. right? So there's not something where just some people think, ah, there's a CPU in this Apple laptop and there's a CPU maybe there, and we put that back and basically chink that together. There's a highly specialized industry creating basically for these racks the different parts in it. So that is definitively not something where just people just pulling things together. And this, of course, has enabled now lots of different elements. Here's another example of a Google data center where you see, again, the infrastructure, right, with cables for fire. Basically, there's a big infrastructure here, second floors, things we see also in the video. But the bigger the data center is, we also have to think about now the downside, right? The upside, lots of money, cool. Lots of users, cool. The problem is it's just simple hardware in the end. It will always fail, right? So basically, when you look at this picture, you see that basically in every rack will be an error again and again, basically over time. Some people fix that. You see that sometimes with rollers, and so they roll through that and then basically exchange some of these parts of the rack. But the problem is the software has to follow through. And that's something what we also learn in the Hadoop distributed file system is basically assuming error by default, right? So there's a certain resiliency that the data centers have now. Virtualization was helping there, as we have seen this live migration. So the workload can be directly transferred very quickly away from a failed node, as we would call that. But then, of course, lots of problems that can happen there, and you should know a little bit of these metrics. I go through them a little bit more quicker, though, but yeah, I think these are metrics which are usually known, but in a way also easy to understand. Before we go there, just take away the message that usually we have also this DRUPS, this kind of uninterruptible power supplies, which is not really true. They are requiring diesel, and also diesel at some point in time is empty, right? So the big diesel tanks that fill these, and basically they would enable at least here and there some data centers to operate further. When the main power shortage is, or basically the power lines are broken, you can operate this. Some of you know that here in Iceland, at least basically in previous times, like Bolungarvík, when over the pass or over the mountains, the power lines are basically not anymore working, then everything is dark in the city, but usually the city would have UPS, right, to get at least parts of the city done. Bolungarvík is a good example. They have actually just received, I think, 4 new diesel generators for that, and lots of oil tanks, basically, or diesel tanks. So this is the same way how you do it in the kind of work that you do in data centers. These days, however, I have to say, it's hardly possible to keep the data center long alive, right? Because we have so many, economics of scale. We have seen 11 times a soccer field. That means you can just operate it for a couple of hours and then you're basically also in trouble. Of course, you can have more people giving you more diesel and tanks and whatever. But in the end, we cannot do this anymore of saying, well, we just operate diesel and then it will take care of the whole infrastructure of the IT. But the good thing is it at least enables us to downgrade the workload, to maybe shift workload to other data centers, which is important to do as well. Right, so I just talk a little bit about here the idea how this is all fueled and cooled. This was one idea where you see how that works in terms of cooling. You have a second floor and you inject essentially the cold air basically from the bottom. It will be heated up through the racks, which is all the computers, and then sucked in again, basically. This could be helped with liquid support. So also here, I said water cooling is something where you can basically think about that. In a way today, there are very different ways how you can do it, and then use maybe this liquid even for city heating, as I discussed. From the network perspective, also, of course, there are really large networks of fat tree switch, which might be, basically leading to also errors when one part of the network is not really existing anymore. But you see here, even if a switch is basically crashing, sometimes they have basically the ability then with dual switches to reach still the data center. Of course, the throughput and the bandwidth would be basically reduced. But also here is something to consider. This is something which is in data center design, very important. And also there you have different topologies, which will require us more different lectures, but that's not what we really want to do here in the course. We keep that to a moderate degree. There are different ways how you can share with a NAS, LAN, and SAN. So it's basically optimized for disks, for large machines on storage. Also there, you would basically have different ways how you do it. Again, it's not like you would consider just piling up those. highly optimized storage disks, and so on. And of course, on top of it, as I said in one of the earlier lectures, also tape archives these days. Some metrics, we take some of them up again in other further lectures. So of course, scalability of size, software scalability is something to think about. Then you would have application scalability. So you basically can scale up your application more and more. That is, of course, something which is nice, essentially, for all the data centers. And then technology scalability, while you have old GPUs, you update to new GPUs as possible and things like that. So in the end, very nice ideas of scalability. You don't need to know all of them by heart, basically, in this data center metrics. Towards the end, just shortly, what is a public, private, and hybrid cloud? This is now the sharing aspect, right? So again, as I said earlier, you have a private cloud with medical data you don't want to really share. You have a public cloud where you want to compute. So the idea is maybe that some of the things from you, not the medical data itself, but some models and machine learning, which are basically just mathematics in the end, so it has nothing to do anymore with the medical people. You basically have analyzed, this is something you can share as a mathematical model. If that is basically in the cloud, nobody knows which the patient it was trained from. So here's a combination, a smart combination that we will also again and again visit in lecture 8, 9, and 10. Good. I think at the end, just one video, if you have to go to the next lecture, because we started a little bit late, is also the problem. Everything is recorded. But I think it's a nice video showing you again how basically the Google data center works. And of course, our walk to the Borealis data center would be quite much more interesting, where you really can touch metal. So let's have a short video.
A data center's the brains of the internet.
The engine of the internet.
It is a giant building with a lot of power, a lot of cooling, and a lot of computers.
It's row upon row upon row of machines, all working together to provide the services that make Google function.
I love building and operating data centers. I'm Joe Cava, Vice President of Data Centers at Google. I'm responsible for managing the teams globally that design, build, and operate Google's data centers. We're also responsible for the environmental health and safety, sustainability, and carbon offsets for our data centers. This data center here in South Carolina is one node in a larger network of data centers all over the world. Of all the employees at Google, a very, very small percentage of those employees are authorized to even enter a data center campus. The men and women that run these data centers and keep them up 24 hours a day, 7 days a week, they are incredibly passionate about what they're doing.
In layman's terms, what do I do here?
I typically refer to myself as the herder of cats.
And I'm an engineer, hardware site operations manager.
We keep the lights on.
And we enjoy doing it.
And they work very hard. So we like to provide them a fun environment where they can also play hard as well.
We just went past the 3 million man-hour mark for zero lost time incidents. 3 million man-hours is a really long time, and with the number of people that we have on site, that is an amazing accomplishment.
I think the Google data centers really can offer a level of security that almost no other company can match. We have an information security team that is truly second to none. You have the expression, they wrote the book on that. Well, there are many of our information security team members that have really written the books on best practices in information security. Protecting the security and the privacy of our users' information is our foremost design criteria. We use various layers of higher level security the closer into the center of the campus you get. So just to enter this campus, my badge had to be on a pre-authorized access list. Then to come into the building, that was another level of security. To get into the secure corridor, which leads to the data center, that's a higher level of security. And the data center and the networking rooms are the highest level of security. And the technologies we use are different. Like for instance, in our highest level areas, we even use underfloor intrusion detection via laser beams. So I'm going to demonstrate going into the secure corridor now. One, I have to be on the authorized list with my badge. And then two, I use a biometric iris scanner to verify that it truly is me. Okay, here we are on the data center floor. The first thing that I notice is that it's a little warm in here. It's about 80 degrees Fahrenheit. Google runs our data centers warmer than most because it helps with the efficiency. You'll notice that we have overhead power distribution. Coming from the outside yard, we bring in the high voltage power distributed across the bus bars to all of the customized bus taps that are basically plugs where we plug in all the extension cords. All of our racks don't really look like a traditional server rack. These are custom designed and built for Google so that we can optimize the servers for hyper efficiency and high performance computing. It's true that sometimes drives fail and we have to replace them to upgrade them because maybe they're just no longer efficient to run. We have a very thorough end-to-end chain of custody process for managing those drives from the time that they're checked out to the server till they're brought to an ultra-secure cage where they're erased and crushed if necessary. So any drive that can't be verified as 100% clean, we crush it first, and then we take it to an industrial wood chipper where it's shredded into these little pieces like this. In the time that I've been at Google for almost 6.5 years now, we have changed our cooling technologies at least 5 times. Most data centers have air conditioning units along the perimeter walls that force cold air under the floor that then raises up in front of the servers and cools the servers. In our solution, we take the server racks and we butt it right up against our air conditioning unit. We just use cool water flowing through those copper coils that you see there. So the hot air from the servers is contained in that hot aisle. It raises up, passes across those coils, where the heat from the air transfers to the water in those coils, and then that warm water is then brought outside the data center to our cooling plant, where it is cooled down through our cooling towers and returned back to the data center, and that process just repeats over and over again. To me, the thing that amazes me about Google in the data centers is the pace of innovation and always challenging the way we're doing things. So when people say that innovation in a certain area is done, that we've kind of reached the pinnacle of what can be achieved, I just laugh.
So it's all about fun at Google, right? Again, of course, I'm not funded by Google. Take it away, but this was a quite good insight, I hope. Thank you very much for staying. We will continue on Thursday then with lecture 5, and as we discussed, with a quiz. Thank you.